again, if we want to determine discontinuity, we have to calculate for the right hand and left hand limit, and we compare these two one-sided limits. So let me show you. So essentially, if both limits are observed to exist but they are not equal, so that's a finite jump, like I said earlier. So the condition for that is both limits exist from the right and left hand limit, but they're not equal. For example, 4 is not equal to 3. So, but then if both limits approach positive or negative infinity, then there is an infinite discontinuity for as long as infinity is involved. From my observations, I think that's the case. So if both limits are equal, then you check if f of a is undefined. If f of a is undefined, then there is a missing point. If f of a is defined, well, and this condition is met, I believe this is the third one, the third condition. Therefore, it is continuous at A. So, yeah, that's basically it. Okay, so we've got some sample problems to work on. So these are the instructions. You know what? I'll just show you. I'm not gonna write them down anymore. This is less practical. So determine the points of discontinuity and you classify them. You give the equation of the vertical and horizontal asymptote, granted that they exist. You define the function at point where there is a missing point, discontinuity. You sketch the function graph. You give the domain and range. So yeah, those 5 instructions. We'll be having this first question. I'll write it down. So y is equal to 2x minus 4 over x squared minus 4, such that x is supposed to be less than 4. We have another, so that's going to be x minus 4, such that x is greater than or equal to 4. So let's work on this one first. So at x is less than 4, y, we want to just work on the denominator. So try to factor the entire fraction first. See what can be cancelled. In the denominator, this could be rewritten as this. So clearly we can cancel something. But before that though, actually this is not just an if, we want to find the points of discontinuity first. So we copy exactly whatever is in the denominator before factoring anything. Before cancelling anything. We equate it to 0, and then we solve for x. So 1 is going to be positive 2. The other is going to be negative 2. So these are the points of discontinuity, at least coming from this rational function. So what we want to do now is, find the limit as x approaches negative 2 using this. We'll be using positive 2 later. So 2 times x minus 2, we just copy this entire thing and then we start factoring from there. So cancel 2 over x plus 2, and then substitute negative 2 plus 2, 2 over 0. In the previous video, it was said that if we have a constant over 0, I think I mentioned it was supposed to be positive infinity, which it is. So that's just the way it is. If you see something like this, it's automatically positive infinity. So that's just in general. What if this time we want to look for the limit? So LHL and RHL, left hand and right hand respectively. So just copy this, but this time put a symbol that says left hand, so coming from the left. You do the same thing. So this time you just copy this, the cancelled, the more simplified version, and substitute. Since this is this, by the way, is gonna be 0, and you copy the left hand sign, so this is gonna be equal to negative infinity. Take note. How about for right hand limit? So 2 over x plus 2, 2 over 0 plus, that's gonna be positive infinity. Okay, so clearly this indicates that we have an infinite discontinuity, where at x is equal to negative 2, this is where the vertical asymptote is. So this time at x is equal to 2, so limit as x approaches 2 of 2 over x plus 2 is equal to 1/2. So we already checked that x is equal to 2. What about the left hand and the right hand limit? This is sorry about that. It's going to be 4. Doesn't make much change. For as long as this is not going to equal to 0, you don't copy the left hand sign. So there's no left hand sign in the answer itself. It is not infinity anyways, so that makes more sense. Okay, same thing. So what is indicated here? So the limit of y or f of x, y and f of x are usually interchanged, but they're essentially the same thing. So from the left and from the right, they're equal. What if we directly substitute 2 as x? So f of 2 in, let's copy this exact thing again. Sorry. So 2 times 0 over 0 times 4. That's equal to 0 over 0. It is an indeterminate form. Therefore, f of 2 is undefined. Since f of a is undefined, so we could say that there is a missing point discontinuity at x is equal to 2, since we substituted x as 2. So we want to find the domain and range, although usually this is no longer required. I mean, at least in the test, it was no longer required to find. But we'll work on that later anyways. At this time, so we're already finished with this. How about the other one? So first things first, at x is equal to 4. So the limit as x approaches 4 from the left of the function. So 2 times so that will be equal to 6, 1 over 3. How about from the right? Let's substitute already. It's already written here anyways. So 4 minus 2 is 2. 2, 6. Wait. So early. We're not going to use the same function for the right hand limit. What's the logic behind that? Okay. So let me just remind you that looking back here, so coming from the left, any value that is less than 4, it fulfills, it makes this, the use of this function appropriate. But if we consider values greater than 4, we use this because the condition there is that x is greater than or equal to 4. So we use this. So substitute, so 4 as x and then just copy minus 4. It is equal to 0. Therefore, since the left hand and right hand are not the same, so we could say since the one-sided limits are not equal, we have a finite jump discontinuity at x is equal to 4. Okay? Now let's identify the asymptotes. So for VA, or vertical asymptote, we already found that out a while ago when we identified what our infinite discontinuity was. So at x is equal to -2, that's where our VA is, since we have an infinite discontinuity there. What about horizontal asymptote? So this is something that you'd want to know. So there are 3 conditions. If the numerator of I think I've mentioned this in previous video. I won't discuss it anymore. I'll just discuss whatever is relevant to our case right now. So in the function y is equal to 2 over x plus 2, this is the simplified one, by the way. the one where we factored and we cancelled. So since the degree of the denominator, it's a polynomial, it basically the term that has the highest degree, which is raised to 1, above is just raised to 0 because it's a constant. But essentially, since the denominator's greater than that of the numerator in that sense, so let me just write it down. Since n is greater than n in y is equal to 2 over x plus 2, under the condition x is less than 4, HA for x less than 4 is y is equal to 0. Okay, so that only applies. We all know that HA is 0 if this condition is met. Let's look at the case of our other function. So under this condition, so we have a polynomial function. There's no fraction. So obviously, the degree of the numerator is greater than that of the denominator. So HA for the condition x is greater than or equal to 4 is non-existent. Let me give you, just to complete all definitions that you'd want to know. So let's say n is equal to m. So the degree of the denominator is greater than the degree of the numerator. So essentially both are raised to 1. So in that case, the HA is going to be 2 over 3, whatever their coefficients are. So write it as a fraction. But again, this is not part of the actual scenario. We only found 2 horizontal asymptotes. So what do we do with the asymptotes? Before we start graphing, this is what we do. So y is equal to 2 over x plus 2 at x is equal to 0. If we substitute x is 0, so it's going to be 2 and it's going to be 1. So 0, 1. This is one of the things that we would see in its actual graph. So that helps give us a better idea of what the graph would look like. So how about at x is equal to 4? We use the same fraction, so this time substitute x as 4, 6, 1 over 3. Okay, so 4 and 1 over 3. Okay, so let's start graphing. Where are our vertical asymptotes? So let's say negative 2 is over here. Draw the vertical asymptote there. Horizontal asymptote, so we have y is equal to 0. And then what else? 4 and 1/3. This is 4. 1/3 is over here. Actually, this is supposed to be an open circle. 0, 1. infinite jump discontinuity at x is equal to 4. Okay. So it appears to be that the graph is definitely not going to look like this. Maybe in the other way around, since we have points here. It has to look like this. And then, how about our... Let's try finding more points. X is greater than or equal to 4. Y is equal to x minus 4 at x is equal to 4. So let's say we substitute 4 as x. So we have 4 and 0. How about at x is equal to 5? Y is equal to 1. So 5, 1. Okay, so we have 2 more points. 4, 0 and 5, 1. So that is another part. Definitely, since we have infinite discontinuity, we have another written like that. So yeah, that's it. That's our crude graph. How about the missing point discontinuity? At x is equal to 2. How do we write that down? So somewhere here, we have a missing point discontinuity. And our finite jump discontinuity is located at x is equal to 4. 4 is right here. So there's a jump. Okay. Okay, so let's find the domain and range. So for the domain, coming from the left, we come from negative infinity until we reach negative 2. And then we rewrite negative 2, and then we reach until positive 2 because there is another gap. And then another set union, 2, and then positive infinity. That is for the domain. How about the range from down to up? So it is recognized that we do have a horizontal asymptote at 0, right? Even so, the range is described to be negative to positive infinity. So 0, this is excluded in the range of x is equal to, x minus 4 in the condition x is greater than or equal to 4. So, but then since the horizontal asymptote is 0, it is technically supposed to be part of the range. So yeah, I think that's one of the conditions you also have to consider. It just so happens that it's like that. It doesn't change. That's always the case. Okay. Next question. So we have x squared minus 4, 1 over x minus 5. So let's start. At x is greater than or equal to 0, y is equal to 1 over x minus 5, right? We always use the fraction when we want to identify the points of discontinuity, not the polynomial one. So again, copy the denominator, equate it to 0. So that is our point of discontinuity. Let's identify if there is an infinite discontinuity. So as x approaches 5 of this function, let's try to substitute directly. So constant over 0, that's going to equal to a positive infinity. Let's identify the left hand and right hand limit. So for the left hand limit, this is negative infinity. How about for the right hand? This is going to equal to positive infinity. So therefore, we have an infinite discontinuity at x is equal to 5. So this technically is also going to be our vertical asymptote. So, okay. When I tried answering this problem myself, I realized that you don't have to look for the missing point discontinuity because it doesn't exist. But I'm still not sure why it's like that. Next, at x is equal to 0, ooh, okay. I just remembered something that is a mistake from my professor. So apparently this is supposed to be 2, not 0. Both of them. So we cannot say at x is equal to 0. It's supposed to be at x is equal to 2. So the limit of y as x approaches 2 from the left side so any value that is less than 2, it fulfills this condition. So we use this function, 2 squared minus 4 . Well, that's going to just equal to 0. What about from the right side? So that is going to be, well, what fulfills the condition that x values are greater than 2 is this. So we use this function, the rational. So negative 1/3. Since the limit of y as x approaches 2 from the left side is not equal to the one approaching from the right side, so it is identified. But since one-sided limits are not equal, we have a finite jump. At x is equal to 2. Okay, let's identify the asymptotes. So for the VA, well, that's already x is equal to 5, since we found an infinite discontinuity there. This time, let's find HA. So for x is less than 0, x cubed minus 4 since it is not a rational, it is a polynomial. In other words, the degree of the numerator is greater than that of the denominator. So your y is equal to 0. Sorry. You have no HA, basically. But for x, sorry, this is supposed to be 2. For x is greater than or equal to 2, 1 over x minus 5, since the degree of the denominator is greater than that of the numerator, it has an HA, which is 0. So before we start graphing, let's find points that could be useful. So for x is less than 2, let's say at x is equal to 2, for this one, y is equal to 0, so 2, 0. Let's say at x is equal to 0, y is equal to 0 squared minus 4, negative 4. So 0, negative 4. At x is equal to negative 2, y is equal to 1. 4 minus 4, y is 0. So negative 2, 0. So those are 3 points. How about for x is greater than or equal to 2? So 1 is equal to 2 minus 5, negative 1/3. Okay, let's start graphing. 2, 0. 0, negative 4. Negative 2, 0. Okay, so I think there is a parabola. It makes sense because squared. So this is a quadratic. I think it is. Is it a quadratic? It looks like. What else? Infinite discontinuity at x equal to 5. 3, 4, 5. Somewhere here. So that is where the vertical asymptote is. What other details? Y is equal to 0. Okay, we have a horizontal asymptote here. Finite drop discontinuity at x is equal to 2. Okay. Finite jump. Yeah, I think this is the one. 2 and negative 1/3. Okay, I think it starts to make sense. There you go. So that's what it looks like. So just from that kind of detail, knowing that there is a finite jump there, there's an infinite discontinuity somewhere there, and we have a quadratic, and it appears to be that it's basically there is a local minimum here. So you're able to identify that the graph is not supposed to look like this for the infinite part. it's supposed to look like that because of this point. It makes more sense, if you get what I mean. So let's identify the domain and range. So from the left, so we have negative infinity until, well, this is still technically part. Don't get that wrong. I got it wrong in the first place. We stop here. So write 5, union 5, and then positive infinity. What about the range? So coming from the bottom, so negative infinity. Apparently, the range is said to be this. I don't get it. I don't get why. Okay, it makes sense that there are brackets. There's a bracket for this part since there are no open circles so far. But here it's a parenthesis. And -4 to positive infinity. Yeah, again, I don't really get why this is the range. But that's it. Okay, I'm not gonna tackle the next question. Actually, that's the last question, but both of them are rational functions. I still need clarification from the prof, even if the term is already over. I'm just gonna skip that part. Okay, that's it.